Chapter 1, Section 3. We have several objectives in this section. First, use function notation to represent and evaluate a function. Find the domain and range of a function. Find the combinations of functions. Find the inverse function. Find the symmetry test of functions. Classify the trigonometric function. Lastly, identify and solve different types of transformation of functions. A relation between two sets Bx and By is a set of ordered pairs, each of the form xy, where x is a member of Bx and y is a member of By. A function from Bx to By is a relation between Bx and By that has the property that any two ordered pairs with the same x value also have the same y value. The x variable is independent variable and the y variable is dependent variable. Definition of a real value function of a real variable. Let Bx and By be sets of real numbers. A real value function f of a real variable x from Bx to By is a correspondence that assigns to each number x in Bx exactly one number y in By. The domain of f is the set Bx. The number y here, number y is the image of x under f and is denoted by fx. Is a function which is called the value of f at x. The range here is a range of f is a subset of By and consists of all image of number in Bx. Functions can be specified in a variety of ways. However, we will concentrate on functions that are given by equations involving the dependent and independent variables. For example, x squared plus 2y equal to 1. We say this equation in implicit form because the x variable and the y variable are at the same place. They are at the left side. And y we call dependent variable. And for the x variable, we call independent variable. To evaluate this function, it is convenient to isolate on the left side of the equation. Okay, so look at here. This is a original equation. Okay, in our last previous page. Okay, so in this implicit form. Okay, then you solve. Okay, the equation for y. So you obtain this. How you solve is you arrange. Okay, just rearrange the variable. Okay, you move. Okay, the x squared to right side, and then you move the constant to right side. Then you obtain y equation. So this equation we call in explicit form. After you obtain the explicit form, you change the y to fx. So we obtain function notation. look at the first example. For the function f defined by fx equal to x squared plus 7, evaluate each expression. For the a, we have f3a. Okay, so you replace the x by 3x. So you will have 3a squared plus 7. You expand the 3a, so you have 9a squared plus 7. For b, f b minus 1. Same. Okay, the method is same, still the same. You replace the x by b minus 1. So the x here replaced by b minus 1. So here also b minus 1. So you got this, okay, expression. Okay, then you expand the b minus 1 square. Okay, so this is a expansion. Okay, this is an expansion. Okay, then you simplify. For c, we have f x plus delta x minus original function divided by delta x. Okay, so for this function, okay, you replace, okay, the x by delta x, okay, into the original function. So we have x plus delta x squared plus 7. Okay, then the rest you remain. Okay, then this one for the original function, make sure you put the bracket because later you need to expand in the minus, okay, the negative sign. Okay, then you expand, okay, the x plus delta x squared. Okay, so this is the result of expansion. Okay, the result of expansion. Okay, and after that you expand in the negative sign. Okay, so we have negative x squared and negative 7. And you can simplify. Okay, after you simplify, okay, you can factorize out delta x. Okay, then you simplify the delta x. So lastly, our answer is 2x plus delta x. And you need to state the delta x not equal to 0. Because of when the delta x equal to 0, so this expression is undefined. The domain of a function can be described explicitly or implicitly by an equation used to define the function. The implied domain is the set of all real numbers for which the equation is defined. Various and explicitly defined domain is one that is given along with the function. For example, fx equal to 1 over x squared minus 4. And the domain given is x between 4 and 5. Has an explicitly defined domain given by this form. So you can write the domain as this form. You open the curly bracket and you write the x and then semicolon and you write the domain of x. So this is the way we write domain. For this function, gx equal to 1 over x squared minus 4. So without domain given, so you can say that this function has an implied domain. That is the set. You open the curly bracket, you write x, then semicolon, and x not equal to plus minus 2. This is because when you substitute x, okay, equal to 2 or the negative 2 here, so you will have 1 over 0. So meaning that the function is undefined. Sketch the graph for each of the following functions and determine its range. Okay, so you have a two function here. So the first function is a linear function and the second function is quadratic function. Both is given domain. For the domain of A part, okay, the x is from 1 to 3. But for the domain of B, from -2, but exclude -2 to 1. To obtain the range of the linear function, you can straight away to substitute the domain into the function. So you just replace the x by 1 and you have -1, and you replace the x by 3 and you have 5, and you can conclude your range. So the range of function is equal to, you open the curve bracket, y semicolon from -1 to 5. And you also can refer to this figure. So this is a linear function. And I show you, okay, where is the domain? So the domain given for this function is from 1 to 3. So you look at the domain here, okay, the x interval, okay, on this function. So in this domain, for the linear function, for this linear function, the range is from -1 to 5. And for the another way to determine the range, you can start from domain. So this is a given domain. Then this x is a domain. X is a domain. You need to convert this x, the domain, to range. Okay, so we start from this step. Now you multiply by 3. You multiply by 3, so we have x. Multiply by 3, so we have 3x. Then after that, you minus 4. So you minus 4. So lastly, you obtain the 3x minus 4. Okay, you have a 3x minus 4, and where the 3x minus 4 is our fx. Is our fx. So you can change this to fx. Where the range is the output, is fx output. So you can conclude your answer. Okay, your range is from -1 to 5. And you can see the answer same as using this way. Okay, besides from you write your answer in this form, you also can use bracket system, where y is include -1, so you use square bracket, as well as for 5 also included. So let's say 5 is not included. So here you need to use round bracket. Just for example, I show you. For example, y is less than 5 and greater or equal to -1. So if you want to use bracket system, so -1 included, but y exclude, round bracket. For quadratic function, you need to perform the completing the square. So this function has a minimum point at -1, 2. Why you say this is a minimum point? Because the leading coefficient of this quadratic equation is positive. After you obtain a minimum point, you substitute the domain given into the function. It's from -2. You substitute the -2 into the function. You got 3. and then you substitute 1, so you have 6, and then you can conclude your answer. So since you have minimum point, so your range should be from minimum point. Range is y, so you take 2. Okay, take the value of 2. It's not take the -1. -1 is the x coordinate. Okay, you take the 2. So start from 2 to maximum, to the highest point. So the highest point is at 6. Okay, 6. So now you can conclude your answer, or in bracket system. Okay, so this is a curve. Okay, so this is a curve. Now you can see the interval. Okay, the domain of x is from -2 to 1. -2 to 1, and then for the -2 is exclude. Okay, so it's exclude, so that's why it's not shaded. And for 1 is include, so it's shaded. Okay, then you cannot conclude that. Okay, the range is from the 3 to 6. You cannot conclude. So based on this graph, you see, if you say the 3, this is -2, your output is 3. If you conclude your answer is from 3 to 6, so this is wrong. You can see the range suppose start from this point, 2. And why we include the 2? Because the minimum point is on curve. So we include 2. A function r defined by rx equal to 1 over x is a rational function where x not equal to 0, because 1 over 0 is undefined. And we also can call this function as reciprocal function. Since the expression 1 over x represents a real number for all real number of x as set x equal to 0, therefore the domain of function r is a set of all real numbers f set x equal to 0. To obtain the range, you need to get the asymptote line. We have two types of asymptote line. First is horizontal asymptote, and the second is vertical asymptote. To get the horizontal asymptote, let the coefficient of the highest power of x equal to 0. And to get the vertical asymptote, let the coefficient of the highest power of y equal to 0. And for the range of this rational function, you can refer to this graph, and you can sketch out this graph by the method that you have learned in first section. You contract table and you plot. This is how the graph look like. And this is a range. Y is not equal to 0. Sketch the graph for the following rational function and determine its range. Fx equal to 1 over x minus 1, x not equal to 0. So meaning that when x equal to 1, if you substitute x equal to 1 here, so you will have 1 over 0, where this function is undefined. So now the first step, this is a given function, fx equal to 1 over x minus 1, and you change the fx to y. And the whole equation you multiply by x minus 1 at both sides, and you obtain this equation. So from this equation, you can obtain the horizontal asymptote, where you let the coefficient of x, where the coefficient of x is y, equal to 0. So y equal to 0 is horizontal asymptote, meaning that at here, horizontal asymptote. And to get the vertical asymptote, you have to let the coefficient of y from our theory. How to get the coefficient of y? From this equation. You factorize out the y, so you will have this equation. Then the x minus 1 will be our coefficient of y. Then you let equal to 0, and you can solve this equation where the x equal to 1. So x equal to 1 is vertical asymptote. This is a x equal to 1, it's vertical line. And this is a graph of a function of a graph. So you can conclude your range. So based on the graph here, you can see the y is value for all the value, the y. Look at the y, and disconnected at y equal to 0. And here is valid, is exists the y. So you can conclude your range. Y is the element of real number, but y not equal to 0. F set y equal to 0. A function f defined by fx equal to radical ax plus b, where x greater or equal to negative b over a. A and b are real constant. It's a radical function. The domain is the set of all real numbers x, such that radical ax plus b is a real. That is ax plus b greater or equal to 0. This is because ax plus b inside the radical, the value must be equal to 0 or positive value. For example, radical 0 is 0, radical 1 is 1, is defined. If ax plus b, the value here is negative value, for example, radical negative 1, so it's undefined. So that is why ax plus b must be greater or equal to 0. And so we have x greater or equal to negative b over a, which is the largest possible domain of f. And after you obtain the x value, so you can write your domain in this form. The graph of a root function is upper half of the parabola symmetrical about the x-axis with the vertex at the point negative b over a 0. So this is a curve of radical function. The curve is upper half of parabola, symmetrical about the x-axis. And this is a vertex point at negative b over a. It's an x coordinate. So on x-axis, so y is 0. So you can look at the range. So the range for this radical function is valid for from 0, okay, start from this point, from 0 to infinite. The example of radical function, sketch the graph of fx equal to radical x minus 1 and determine its domain and range. The domain of the function is set of all x value for which x minus 1 greater or equal to 0. So you solve. You bring the negative 1 to right side so that you will have x greater or equal to 1. Then you can write it into the bracket system. 1 to infinity. Then 1 is included. And for the graph part, you can use the method that you have learned in first section. You contract a table, then you plot. This is a curve of this function, and based on this curve, you can see the range. Start from this point, so you touch on the x-axis, so y equal to 0, and this is a range of y. Okay, the range. So it's until the infinity. The domain of the tangent function fx equal to tangent x is the set of all x values such that x not equal to pi over 2. Here is the point, pi over 2. You can see here is a asymptote line. And you can verify this point by using your calculator, where tangent 90 degree is undefined. And not only for the 90 degree, but for the 270 degree and so on. So that is why you need to write your solution in general solution form, where x not equal to pi over 2 plus m pi. The pi here, because of tangent, the period of tangent is 180 degree, and n is an integer. Proof, okay, the point. So for example, the first point, pi over 2 here, when n equal to 0. So the first point is pi over 2. When n equal to 1, so you will have 3 pi over 2 here. And if n is equal to 2, so you will have 5 pi over 2, which is here, and so on. So since you have infinite solution, you have to write your solution in general solution. The absolute value function can be defined using the definition of absolute value. If you have one function is equal to absolute value of x, you can break it down to piecewise function, where the fx equal to x if x is greater or equal to 0, and fx equal to negative x if x less than 0. And notice that this function is defined by different formula for different parts of its domain. So that you can see here, you have two different formula equation here and have their own domain. And the range of this function is y greater or equal to 0. Sketch the function defined by fx equal to x plus 2x over absolute value of x and find its domain and range. This function involves rational function and absolute value function. By using the definition of rational function, we know that the denominator of rational function cannot equal to 0. So x cannot equal to 0. While in piecewise definition of absolute value of x, for positive side, we just can state the x greater than 0, not include the 0. So our fx equal to x plus 2x over positive x. Okay, because of here x. Then we simplify, we have x plus 2. And for the negative side, x less than 0. Then we have absolute value of x equal to negative x. And we substitute into the given function and we simplify, we have x minus 2. So we obtain piecewise function. Okay, and also the domain for each equation. piecewise function, you can plot the graph out. The graph, you can obtain the domain and also the range. Look at the domain. Domain is on x-axis. You can see the line for this side is axis, and for the positive side is axis. And how about at x equal to 0? Here is excluded and here also is excluded. So you can write your domain of this function. X is element of all real number, but x not equal to 0. And how about the range? The range, you refer to the y-axis. Look at the line here, meaning that this area is axis until the negative infinity. So you can write y lesser than -2. And this area is undefined, so it's nothing. And how about this side? It's defined. There exists the line. So y greater than 2. A function from bx to by is 1-to-1 when to each y value in the range that corresponds exactly one x value in the domain. A function from bx to by is onto if its range consists of all of by. The graph of the function y equal to fx consists of all points x fx, where x is in the domain of f. Figure, x is the directed distance from the y-axis. This is a x, the distance from y-axis. Fx is the directed distance from the x-axis. This is the fx. The height is from x-axis. A vertical line can intersect the graph of a function of x at most once. This observation provides a convenient visual test called the vertical line test for function of x. There is a graph in the coordinate plane. It's the graph of a function of x if and only if no vertical line intersects the graph at more than one point. First figure, we say this graph is not a function of x because a vertical line intersects the graph twice, this point and this point. Where for the second and the third, they are a function of x because when we apply the vertical line test here, there's only one point of intersection. Same for here. If you move along your vertical line test to left or right, there is just only one point of intersection. You can go through these 8 basic functions. The first is linear function, quadratic function, cubic function, square root function, or we call radical function, absolute value function, rational function, sine function, and cosine function. By the end of the 18th century, mathematicians and scientists had concluded that many real-world phenomena could be represented by mathematical models taken from a collection of functions called elementary functions. Elementary functions fall into 3 categories. The first is algebraic functions. Second, trigonometric functions. The third, exponential and logarithmic functions. The most common types of algebraic function is a polynomial function, where n is a non-negative integer. The number ai are coefficients, with an the leading coefficient and a0 the constant term of the polynomial function. If leading coefficient is not equal to 0, then n is the degree of the polynomial function. The zero polynomial fx equal to 0 is not assigned a degree. It is common practice to use subscript notation for coefficients of general polynomial functions. But for polynomial function of low degree, the following simpler form are often used. The 0 degree, first degree, and until the third degree. Although the graph of a non-constant polynomial function can have several terms, eventually the graph will rise or fall without bounds as x moves to the right or left. Whether the graph eventually rises or falls can be determined by the function degree, odd or even, and by the leading coefficient. Look at the two left side graph. Degree, the first graph is positive leading coefficient and the second graph is negative leading coefficient. See, for the even degree, their graph have beginning and the ending of the curve pointing the same direction. For the positive leading coefficient, the beginning and the ending of the curve are pointing out. And for the negative leading coefficient, the beginning and the ending of the curve are pointing down. However, for the function of odd degree, the beginning and ending of the curve are inverse direction. For example, the positive leading coefficient, the beginning of the curve is pointing down, but for the ending of the curve is pointing out. However, for the negative leading coefficient, the beginning of the curve is pointing out, and for the ending of the curve is pointing down. So the leading coefficient test can be used to determine the right and the left behavior of the graph. Just as a rational number can be written as the quotient of two integers, a rational function can be written as the quotient of two polynomials. For example, this is a form fx equal to px over qx, where qx not equal to 0 because rational function, and px and qx are polynomial. Polynomial functions and rational functions are examples of algebraic function. An algebraic function of x is one that can be expressed as a finite number of sums, differences, multiples, quotients, and radicals involving x power to the n. For example, fx equal to radical x plus 1 is algebraic. Functions that are not algebraic are transcendental. For example, the trigonometric functions are transcendental. Two functions can be combined in various ways to create new functions. For example, given two functions fx and gx, you can form the new function. For example, f plus gx. You can take the fx plus gx, then you cover a new function. You can simplify. And same for different product and quotient. You can combine two functions in yet another way, called composition. The resulting function is called a composite function. let f and g be functions. This function is the composite function of f with g. The domain of composite function f(g(x) is the set of all x in the domain of g, such that gx is the domain of f. Look at this figure. You can see this composite function f(g(x). This is a new function, and the domain for this function is domain of g, because this is a g function. And to obtain the composite function f(g(x), we perform the g function first, then followed by f function. The composite function of f with g is generally not the same as the composite of g with f. The composite function f(g(x) uses the output gx of the first g as the input for the second function f. So look at this composite function f(g(x) uses the output gx. This is the output gx out of g function as the input for the second function f. Given two different functions fx and gx, find each composite function f(gx) and gfx. So first, f(gx). As I say, composite function of f(gx), you should perform the gx function first. So you substitute, okay, you replace the gx by cos x, and then you substitute the cos x into the fx function. So we will have 2 cos x minus 3. And you simplify. So this is a result. Gfx. For the gfx, you should perform the f function first. So you replace the fx by 2x minus 3. And then you take the 2x minus 3, you substitute into the g function. Then we have cos 2x minus 3. So the composite function of f(gx) is not equal to composite function of gfx. An x-intercept of a graph is defined to be a point a0 because x-intercept, so line on x exists, so that's why the y-coordinate is equal to 0 at which the graph crosses the x-axis. Okay, so if the graph represents a function f, the number a is a 0 of f. In other words, the 0 of the function f are the solution of the equation fx equal to 0. For example, the function fx equal to x minus 4 has a 0 at x equal to 4. For inverse function, if fx equal to y is a 1-to-1 and onto function, the inverse function of y is equal to x is defined by x equal to inverse function of y and also equivalent to y equal to fx, where x is the element of bx and y is the element of by. So now look at these two composite functions involve inverse function. So inverse function of fx equal to x, and the composite function for x with inverse function of y is equal to y. Okay, now let's prove. For example, for this composite function, we should perform the fx function first. So we perform the f function. After we perform the first function, fx function, we should perform the inverse function. So from this point to here. Then you can see we back to x. And for the second composite function, we perform the inverse function first. So this is the inverse function. So we start from this point. Then we perform the f function. So you can see back to y is equal to y. Here are the guidelines to get the inverse function. First step, find the domain of f and verify that f is the one-to-one. If f is not one-to-one, then inverse function does not exist. Second step, from the equation y equal to fx, solve for x in terms of y. We have x equal to inverse function of y with inverse function as a function of y. Third step, interchange x and y. We have y equal to inverse function of x with inverse function as a function of x. Last step, find the domain of inverse function. Ensure that domain of inverse function same as the range of the original function. The properties of inverse function. If inverse function exists, then inverse function is a one-to-one and onto function. Domain of inverse function must be same as the range of the original function. And the range of inverse function must be same as domain of original function. This example, the function f is defined by fx equal to radical x minus 2, where the x greater or equal to 2. Find inverse function. Since the domain is given, x greater or equal to 2, and you can scale the graph, and you observe f is one-to-one. You can apply the vertical line test. There's only one intersection. Step 2. Let y equal to fx. So you can change your fx to y. So we have y equal to radical x minus 2. And you solve for x. How to solve? You squaring both sides. Then you solve for x. After you solve for x, you obtain the x equation. You proceed to step 3. Since you know you have already obtained the x equal to y squared plus 2, where the x is the inverse function of y. So interchange the x and y variable. It's our step 3. Interchange. Then can be written as y equal to x squared plus 2, where the y is inverse function of x. Lastly, you can write your inverse function of x equal to x squared plus 2. Now we obtain the inverse function. Last step, we have to obtain the range as well. First step, radical function. The range of the function is y greater or equal to 0, where we also have covered the radical function at previous slide. So you have to know that the domain of the inverse function must be same as the range of the original function. So the domain x of this inverse function must be same as the range of original function. Both you can see greater than 0. Okay, because the range is greater than 0, so here must be greater than 0 as well. Okay, for the domain. So you can conclude your answer. The inverse function of x is equal to x squared plus 2, where the domain for this function is x must greater or equal to 0. This is a relation between the symmetry with even and odd. A function is even if its graph is symmetric with respect to the y-axis, and odd if the graph is symmetric with respect to the origin. Okay, and here is the guideline. Okay, how we test. Okay, the odd and even. We say the function is even when we replace the x by negative x and then produce the function that same as the original function. And we can say the function is odd function if we replace the x by negative x and we produce the function is negative original function. This is a sine theta graph for the domain of between negative 360 degree and positive 360 degree. Based on the graph, you can see the range is from negative 1 to positive 1. And this is the curved sine graph looks like. Sine function is an odd function since the graph is unchanged under a 180 degree rotation about the origin. You can verify this function by using this method. I'm going to show you. You can let theta as 90 degree. So f theta since theta equal to 90 degree, you can write sine 90 degree. Where the sine 90 degree is equal to 1, positive 1. And how about you replace the theta by negative theta? So you will have sine negative 90 degree. Which is produce negative 1. We can conclude sine function is an odd function. The function is the periodic function of period 360 degree. Why we call it a periodic function? Because the graph repeats itself after a regular interval of 360 degree. The maximum value of sine theta is 1 and the minimum value of sine theta is negative 1. So this is a range of sine theta. Look at the cosine graph. And the properties of the cosine function. The cosine function is an even function since the graph is symmetrical about the vertical axis. So the vertical axis is y-axis. And you can verify this function, okay, using the method that I shown you in A part. And this function also is a periodic function of period 360 degree. And the range for this function also same as the sine function. It's between negative 1 and 1. For tangent graph, the tangent function is an odd function since the graph is unchanged under a 180 degree rotation about the origin. And you also can verify this tangent function as well. And for all the value of theta, at set theta equal to plus minus 90 degree, plus minus 270 degrees, and so on, because they are asymptote. You can try to substitute the theta 90 degree into this function. You check with your calculator. The calculator will display undefined. This function is a periodic function of period 180 degree, since the graph repeats itself after a regular interval of 180 degree. The tangent graph has asymptote because tangent theta can be written as sine theta over cosine theta, where this is a rational function. And recall back the definition of rational function. The denominator cannot equal to 0. So if cos theta tend to 0, so function will tend to undefined. What are the value for cosine function is 0? So they are the value here, plus minus 90 degree, and so on. So that's why we call that value as asymptote. We have inverse function for sine, cosine, and tangent. You can call them as inverse sine, inverse cosine, and inverse tangent, or arc sine, arc cosine, and arc tangent. This way to describe the inverse trigo is, for example, you take the first figure here, the first graph, the arc sine, meaning that you rotate the original function for 90 degree. The original function of sine x, you can see, can you imagine? The sine x function is continuous and moving horizontally. So you're moving, okay, horizontally. And this axis is a y-axis. But now in inverse function, the y-axis become x-axis. And for the x-axis, the domain now become y-axis, the range. Same for the arc cosine and the arc tangent. The graph of the inverse of trigonometric functions can be obtained by reflecting the graph of respective trigonometric function about the line y equal to x. None of the trigonometric function is a one-to-one function. In order for a trigonometric function to have its inverse function exist, the domain of the trigonometric function has to be restricted. Determine whether each function is even, odd, or neither. Then find the zero of the function. The zero of the function meaning that it's a solution. The function is odd because we replace the x by negative x. So here, the x by negative x and the x by negative x. And we simplify negative x cube we expand for cube, and negative will become positive. And from this expression, you can factorize the negative. So where the x cubed minus x is original function, so can be written as negative fx. So we have f negative x equal to negative fx. So the function is odd function. And obtain the solution of the function. You let the function equal to 0. And you factorize the x, where the x squared minus 1 still can be factorized. And solve for x. this is a graph. So on graph, you can see there are 3 x-intercept. For b, the function is even because when you replace the x by negative x, so we have 1 plus cos negative x, where the cosine function is even function. So cos negative x equal to cos x, where 1 plus cos x is original function. So it's gx. So g negative x equal to gx is even function. And try to get the solution of this function. Now we're going to solve this trigo equation. Line equal to 0. And move the 1, the constant, to right side. And to get the x value, add cos the negative 1. To obtain the solution. This is a general solution because you have infinite solution because of the graph is continuous function. I show you. This is a function 1 plus cos x equal to 0. So you can see the point for the y equal to 0 is pi, 3 pi, 5 pi, and so on. So you can let the n equal to 0, 1, 2, 3, 4, and so on. The last objective. Here I given one function y equal to x squared, the original function, and you should compare this given function with other equations and analyze their operations. Look at the first graph here. Okay, the brighter color here is given function, the original function y equal to x squared, and another function y equal to x squared plus 2. So you can say that the graph, you can see the graph is actually shift outward vertically for 2 units. Where for the second graph, the brighter color also, yeah, you can see is a given function y equal to x squared, and for the new function y equal to x plus 2 squared, where the x plus 2. So you shift the graph to the left side for 2 units. If you have a function is x minus 2, so you should shift your graph to right side for 2 units. Okay, for this operation, you can see original function y equal to x squared, and you have y equal to negative x squared. So this is a reflection about the x-axis. And look at the last one, y equal to 1 minus x plus 3 squared. Function, we have 3 operations. We should perform the operation from the inner part to outer part. So where the inner part is in this bracket, x plus 3. So you move this curve to left side for 3 units. So the vertex point will be here, and second operation will be negative sign. So reflection about the x-axis. So you rotate your graph, so should be okay. It's better I show you. So first operation, your graph should be like this, and then the second operation, this is the first operation, and for the second operation, because it's negative, so it's reflection about the x-axis. This one is the second operation. And for the third operation, you can see +1. So move upward vertically for 1 unit. So you can see the vertex point is at here, right? So you move 1. So this is a vertex point. Okay, so you can see the darker color one is after you perform the third operation. The previous slide show you 3 basic types of transformation: vertical shift, horizontal shift, and reflection. And this is what I have explained on the previous slide from the A to D graph. There are some operations that you may need to go through, but the 3 main shifting are horizontal shift, vertical shift, and reflection.